Hello my dear friends, in this video we'll solve the problem number 2 on analysis of beams. We have learned in the previous videos what are the theory behind their solving the beams problem by using FEM, and one of the problem has solved on UDL load. I'll read out the problem number 2 for the beam shown in figure Q2. Here the figure is given Q2, beam has a fixed on both ends here and then here. At the mid of the span of a beam element, load has been applied which is equals to transverse load 10 kilonewton and moment about the mid of the beam is equals to 20 kilonewton meter. From a first fixed end to the midpoint, length of the element is equals to 3 meter, and from mid towards the right side end of the beam is equals to 3 meter. Total length of the element which is equals to 6 meter. L by 2 is equals to 3 meters has been given. Determine the displacements at the node 2. We need to determine directly as given node number 1, 2, 3. 3 nodes means 2 elements. Element number 1, this one, and then this one is element number 2. We need to determine the displacement at the mid node, that is node number 2, and then internal loads. What is this internal load? We are well known the internal loads in a beam element is shear forces and bending moment. Shear forces and bending moment we need to find out at each node of a beam element, and also we need to find out the displacement at node number 2 q vector, right? If they have not given, also we need to find out a displacement at node number 2 where the forces are exerting. If they have given, it is well and good. We need to identify. If they have not given these values, node number 1, 2, 3, we need to give the name as similar to this. Y means this is a fixed and this one is a fixed. In all degrees of freedom there is no displacement along vertical or transverse direction V1, and there is no moment, and there is a theta 1 is equals to 0, V1 is equals to 0. Similarly we have here V3, why it is at node number 3 is equals to 0, and we have that theta 3 is equals to 0. We need to find out only at node number 2, that is V2 is equals to question mark and theta 2 is equals to question mark at node number 2. Then take Young's modulus 210 gigapascal and B is equals to 0.2 meter and H is equals to 0.4 meters. He has given a cross section as a rectangular beam element, and Young's modulus of the beam element is given 210 gigapascals. Now we got the problem. We'll take the data first, then we'll solve the problem. Take down the data. Is given a fixed beam. Young's modulus E is equals to 210 gigapascals. We need to convert these gigapascals in terms of a Newton per meter square. The dimensions are given in terms of a meters. Then I'll convert gigapascals in terms of a Newton per millimeter. It becomes so 2.1 into 10 to the power 5 Newton per millimeter square. When I'll convert millimeter in terms of meters, we know that 2.1 into 10 to the power 11 Newton per meter square. And they have given B is equals to 0.2 meters and H is equals to 0.4 meters. I have drawn here a given element. This is the given element. The cross sectional dimensions they have given like this. Breadth is equals to 0.2, which is the smallest. Height is largest. H diagram has drawn. Then we will find out by using this data area of cross section, which is equals to B into H. We are well known 0.2 into 0.4. B is equals to 0.2. H is equals to 0.4. That is equals to 0.08 meter square. Similarly, we want to find out the elemental stiffness matrix moment of inertia, that mass moment of inertia with respect to this cross sectional area. I is equals to BHQ by 12. B is equals to 0.2 and H is equals to 0.4 cube. divided by 12 moment of inertia, which is equals to 1.0667 into 10 to the power of 3 meter power 4. Y means meter into meter cube, meter power 4. We know that the units of moment of inertia. I have copied the same value here, and then you can see from the given figure L1 is equals to L2. Why? The two elements has considered node number 1 and node number 2 and node number 3. From node number 1 to 2 we'll call it as a element number 1, 2 to 3 we'll call it as a element number 2. The element number 1 length is a L1, element number 2 length is a L2. Both lengths are same 3 meters. After getting this data, next we'll go with the element. What is the first step of a finite element method? Based on that, we need to define the forces. Without that knowledge, we cannot be defined any kind of forces, right? First, we'll assume how we need to start the problem. We need to start the problem from left towards the right. This is node number 1. Already they have given node number 2 and node number 3. After getting that, at node number 1, what we have? Vertical direction V1, force is F1. Moment we have theta 1 with AF2. Similarly, we have here at node number 2 V2 F3. Moment theta 2 F4. Vertical displacement V3 F5. Moment theta 3 F6. And this is an element number 1. This one is element number 2. Where at each node 2 degrees of freedom is there. So now the given forces are F3 and F4. F3 is a transverse load and concentrated point load. F4 is moment about the node number 2. F4 is moment about the node number 2. Only these two values is given. That means F3 is equals to minus 10 kilonewton and F4 is equals to plus 20 kilonewton meter. Why? The force F3 is applied vertically downwards in a negative y-axis and moment has been applied in a clockwise direction is positive. This we have taken. Now we need to convert this kilo in terms of a newton. How we will convert that? Just I will read here. I have taken in a data. F3 is equals to minus 10 kilonewton is equals to 10 into 10 to the power of 3 kilo. Then it becomes minus 10 to the power of 4 Newton. And then moment that is equals to M2 I have taken. That M2 is equals to F4 at node number 2. 20 kilonewton meter has given. Convert in terms of a Newton meter. 20 into 10 to the power of 3 Newton meter in a clockwise direction. It is a positive. It is a vertically downwards negative. Right? So as usually I have drawn that FE model. I have explained the given problem. Same FE model. What is the first step of FEM? FE model based on the load on a beam. FE model is considered as a 2 elements, has a 3 nodes, node number 1, node number 2 and node number 3, 2 elements E1 and E2. At node number 1, V1 is a transverse displacement due to the force F1. Moment M1 is equals to F2. Due to this moment theta 1 at node number 1. Due to this force F3, transverse displacement V2. Due to this moment rotation theta 2 at node number 2. Due to this force F5, transverse displacement at node number 3 V3. Rotation due to this moment theta 3 at node number 3. We have converted that FE model. Then what is the second step of FEM? We need to find out the elemental stiffness matrix for a given problem. That elemental stiffness matrix for a given problem we have I have given in the last video also. In this video again I'll tell you how to remember this elemental stiffness matrix. 12 4L square. 12 4L square. Diagonal you remember it. Upper triangular element of matrix, and lower to the diagonal we have here 6Le minus 6Le minus 6Le, 6Le here downwards minus 6Le minus 6Le, similar to that minus 12 6Le minus 12 6Le 2L square 2L square. Likewise, I have given the idea in the last videos. Similarly, we have a given beam element converted in terms of a two elements which has E is equals to 1 comma 2. We have a two elements in a given beam element, then K1 is equals to K2. Why means it is a single beam element, but load has been applied at the mid of the beam. Both end is fixed based on the boundary condition and loading condition. We have converted a single beam in terms of a two element by using FEM method. FEM method first step is a discretization. Just we have discretized a given continuum body in terms of a two elements that has a uniform dimensions throughout the body. As usually we know that L1 is equals to L2 is equals to 3 meters, and then E1 is equals to E2 is equals to 2.1 into 10 to the power of 11 Newton per millimeter square, and then I1 I2 is equals to 1.0667 into 10 to the power of minus 3 meter power 4. These are the values are very similar for a given beam element. Now I will consider a element number 1 E1, then this KE becomes K1, EE becomes E1, IE becomes I1, LE becomes L1 cube, and then this LE becomes 1, and rest of the values similar. I will copy this from this matrix, and then I'll substitute the values of this Young's modulus, moment of inertia, and length of the element number 1 for a beam element. Then L1 we have 3 meters, substitute that L1 3 cube, and then Young's modulus E is equals to 2.1 into 10 to the power of 11 Newton per meter square. Moment of inertia I1 is equals to 1.0667 into 10 to the power of minus 3 meter power 4. Similarly, we have length of the element 3 meters. Substitute here, substitute all the values of the L1 in a matrix and rearrange this matrix. We will get a elemental stiffness matrix for an element number 1. I have substituted all the values here in a K1 matrix of element number 1 for a given beam element. Then I will resolve this matrix. When I will calculate the value of this EI by L cube 8.296 into 10 to the power of 6, and then remain same 12 in the matrix. 6 into 3 18, minus 12 remains same, 6 into 3 18, and then again 6 into 3 18, 4 into 3 square becomes 36, minus 6 into 3 minus 18, 2 into 3 square is equals to 18, minus 12, as it is minus 6 into 3 minus 18 12, then minus 6 into 3 minus 18, 6 into 3 18, 2 into 3 square 18, that is 2 into 9, minus 6 into 3 minus 18, 4 into 3 square 36. Now we know that the element number 1 lies between a two nodes, that is node number 1, 2 and 3 we have in a given element, but element number 1 is lies between a node number 1 and 2 that contains at node number 1 transverse displacement V1 and rotation theta 1. Similarly, at node number 2 we have a transverse displacement V2, rotation theta 2. Based on this condition, we will give the row name and column name of the given element. Then with respect to the transverse displacement V1, first row first column name we have given, and with respect to a rotation at node number 1 theta 1, second row second column name we have given. And similarly at node number 2 we have transverse displacement. First we need to consider at node number 2 V2, third row third column name we have given, theta 2. At node number 2 the rotation with respect to this characteristics of node number 2, fourth row fourth column name has a given in a elemental stiffness matrix for element number 1. Similarly, we have K1 is equals to K2. All the characteristics are remain same. Directly I have copied this elemental stiffness matrix here. We have K1 is equals to K2 due to both elements are same cross sections, right? When we'll copy this same matrix, after that give the names of the row and column. Row and column names are not same compared to the previous matrix. elemental stiffness matrix for element number 1. Why the element is lies between a node number 2 and 3. When the element will get start from node number 2 and 3, the characteristics of the rows and column will get changed. See here, node number 1, node number 2 and node number 3, we have element number 1 will get start from node number 1 and ends at node number 2, and element number 2 will get start from node number 2 and ends at node number 3, that is equals to element number 2 is E2, where the characteristics of node number 2 will represented as V2 theta 2 at node number 2, transverse displacement at node number 3 V3, and rotation at node number 3 theta 3. Based on these 4 characteristics, we need to give the row name and column name of the matrix. That is, first I'll consider V2 at node number 2. A stiffness matrix will get start from first row first column, that will depends upon the first row first column is depends upon the V2, and second row second column is depends upon the theta 2. Similarly, at node number 3 V3, third row third column name of the matrix is depends upon the characteristics of a transverse displacement along y direction at node number 3 V3. Similarly, we have a theta 3. With respect to this theta 3, fourth row fourth column name of the element number 2 elemental stiffness matrix. Now we have defined that elemental stiffness matrix name for a given problem. We have found elemental stiffness matrix. After finding the elemental stiffness matrix, step number 3 of finite element method is a global stiffness matrix. How we need to find out? We are very well known. So many problems we have solved on a bars and trusses. Similar task we need to take to get a global stiffness matrix from elemental stiffness matrix. Global stiffness matrix for a given beam element, we have a 2 element global stiffness matrix K is equals to K1 plus K2. We have then K1 plus K2. I'll substitute the value from the elemental stiffness matrix here. I have taken these 2 values, I have substituted here in this matrix, then I'll resolve that one. Now we know that how many nodes we have. We have 3 nodes and each node has 2 degrees of freedom. 3 into 2, which is equals to 6. We have a 6 cross 6 matrix in a given problem, a global stiffness matrix. The global stiffness matrix is 6 cross 6 matrix. Then I'll take a, with respect to a nodal characteristics, V1 theta 1, V2 theta 2, V3 theta 3. We have taken a column. Similarly, V1 theta 1, V2 theta 2, V3 theta 3. We need to represent the row name and column name. After getting the idea of this row and column, right, this common I have taken 8.296 into 10 to the power of 6. Now we need to consider here V1, first row first column, V1 with respect to V1, where it is there. First we need to identify, we have a V1 here in the first matrix, but we don't have in the second matrix V2 we have, right? It will get start from V2. That means we are not supposed to see from here. We need to get all the values from this matrix. We are well known in the previous method. V1 value, first row first column name value 12, first row second column value V1 theta 1 18, V1 V2 value this one, that is the first row third column name minus 12, V1 theta 2 value we have this one 18, V1 V3 value we don't have here, that is equals to 0, V1 theta 3 value that is equals to 0. Similarly, we need to get a second row first column, second row second column, second row third column, second row fourth column, second row fifth column, second row sixth column. We need to get with respect to V1 V2 V3 theta 1 theta 2 theta 3. So we have this one theta 1, where it is exactly is there in a row. We need to identify with respect to row. We have here theta 1, but we don't have a theta 1 here in the second matrix, right? So we need to get all the values from this first matrix. Here we have theta 1 with respect to V1. Theta 1 with respect to V1 we have here 18, and then theta 1 second row second column plus 36. Theta with respect to V2, we have theta with respect to V2 here, that is second row third column minus 18, second row fourth column we know, second row fourth column value is 18, copy it here, that is the theta 1 theta 2 value. Similarly, theta 1 V3 value we don't have here, 0. Theta 1 theta 3 value, there is no values. Second row sixth column, second row fifth column 0 0 we have taken. After that, getting a second row, similarly third row which is depends upon the V2, V1 has over this one, and then we have this V2 with respect to first column, with respect to second column, with respect to third column, with respect to fourth, with respect to fifth and sixth column. We need to get the value V2 we have in the first matrix as well as we have in this second matrix. Two matrix we have a V2. Concentrate on the both matrices, add both the values now carefully. V2 V1 value, third row first column value. V2 is a third row, first column has a V1. Third row first column value is a minus 12. Minus 12 we have taken, but we don't have any V1 here, that is 12 plus 0 minus 12. V2 theta 1, V2 theta 1 we don't have here, but here we have a minus 18 plus 0, that will be equals to minus 18. Similarly V2 value, V2 value we need to get that is equals to in this matrix 12, and similarly we have in a second matrix 12 plus 12, that is equals to 24. Similarly V2 theta 2 value we need to get V2 theta 2 we have here minus 18 again we have here V2 theta 2 plus 18, we'll have minus 18 plus 18 is equals to 0, we have this value. Similarly V2 V3 value, V3 we don't have in this matrix, we have V3 here, V2 V3 value minus 12. Similarly we have next V2 theta 3 value we have 18, V2 theta 3 value 18, and then we'll get a next row, that is fourth row, where exactly the fourth rows are there with respect to theta 2 value. We have here theta 2 V1 value is 18. Similarly theta value is equals to 18, here we have taken as it is 18, and then theta 2 V2 value we have minus 18, and again we have here plus 18, that is equals to 0. Then similarly theta 2 value we have 36 here also we have 36 plus 36 is equals to 72. Theta 2 V3 value we have here minus 18, we have taken here minus 18. Similarly theta 3 value we have plus 18. Similarly we have V3, where the exactly V3 is there, consider it. V3 we don't have any value in the matrix number 1 for element number 1 V3. With respect to this matrix number 2 we have a V3 here, that row we need to select V3 with respect to V1 0, V3 with respect to theta 1 is equals to 0, we don't have any values here in the second matrix with respect to that row and column, and V3 fifth row third column value we have here minus 12, fifth row fourth column value, that is V3 theta 2 value minus 18, V3 value we have 12, V3 theta 3 value we have here 18. Finally you find out for theta 3 similar to that, and you will get the whole matrix. How many numbers of rows are there with respect to the namings what you have given based on the given element. Based on the given element, solve the problem and get the elemental stiffness matrix. After getting the elemental stiffness matrix, make the global stiffness matrix carefully. Read the rows, particular rows, search it in a elemental stiffness matrix, add it carefully, you will get the global stiffness matrix, right? This common I have taken 8.296 into 10 to the power of 6 common, and after taking that when we'll add this matrix we'll get after getting that matrix we'll say as a global stiffness matrix for a given beam element. After getting that global stiffness matrix for a given beam element, a global displacement vector at node number 1 V1 theta 1, at node number 2 V2 theta 2, at node number 3 V3 theta 3. Similarly I have shown in a force diagram F1, F2, F3, F4, F5, F6. We have transverse force, moment, transverse force, moment, transverse force, a moment. We have this is equals to 0. Why? It is fixed at first end, and this F2 is equals to 0, and then this value has been applied vertically downwards, minus 10 to the power of 4 Newton, that vertically downwards at node number 2, and then this we have a moment in a clockwise direction, that is equals to 20 into 10 to the power of 3 Newton meter, and then this force is equals to 0 due to fixed, this moment is equals to 0 due to fixed end. So the forces we have taken at node number 1 all the force and moments are 0, at node number 3 all the forces and moments are 0, At node number 2, the values of moment and forces is given. The force applied vertically downwards minus 10 into 10 to the power of 3 Newton. Moment is applied at node number 2, 20 into 10 to the power of 3 Newton meter. This is the force vector. We got a global stiffness matrix, global displacement vector and global force vector. Then bring that all characteristics in terms of equilibrium condition. KQ is equals to F. Write the global stiffness matrix, global displacement vector and force vector in a equilibrium condition. We have copied this global stiffness matrix, global displacement vector and global force vector. After copying that one, we need to apply the boundary condition. We are very well known how to consider a boundary condition. We have solved several problems based on that concept. It is very easy to define. See, at node number 1 we have theta 1 and v1, that is equals to 0. Why it is fixed? At node number 3 we have v3 and theta 3, both are is equals to 0, but v2 and theta 2 are not equals to 0, that is equals to question mark. Why it is free and forced, right? So based on these two conditions, we need to eliminate row and column in a matrix. You can check out. I'll eliminate with respect to v1 theta 1, v3 theta 3 is equals to 0 by using an elimination method. First row, first column we'll eliminated. Then with respect to v1, with respect to theta 1 eliminated. With respect to v3, fourth row, fourth column has been eliminated. With respect to theta 3, fifth row, fifth column has been eliminated. Rest of the values we have, I have written in a square box. This is 24, 0, 72, v2 and theta 2. Minus 10 into 10 to the power of 3, 20 into 10 to the power of 3. These are the values we need to take. After applying the boundary condition, 6 cross 6 matrix is reduces to 2 cross 2 matrix. Then this 8.296 into 10 to the power of 6 I have taken common. This value I have copied. 24, 0, 0, 72. v2 theta 2 I have copied, and then minus 10 into 10 to the power of 3 plus 20 into 10 to the power of 3. Now we have a 2 cross 2 matrix. We are very well known. Use the calculator. Enter the values of this matrix. A1, B1, C1 value, A2, B2, C2 value. In your calculator, go in a mod button, select the two unknown equation, enter the values in that calculator, put it a equals button. You will get a x value, that is equals to v2, and y value is a theta 2. X value what we have in terms of a meters, y value what we have in terms of a radians. Y x is depends upon the transverse displacement v2, and y value is depends upon the rotation of a beam element at node number 2. The rotation is representing in terms of a radian, and transverse displacement is representing in terms of a meters. Now we got all the values at node number 2 as per the given problem statement. The statement has given in your problem. Cross verify it. He has asked to determine the displacement at the node number 2. We have to find out the displacement at node number 2, that is equals to theta 2 and v2. We have found these two values. After getting the two values, we need to find out the internal forces. Displacement vector q is equals to 0, 0. Then displacement occurs in a transverse direction at node number 2, minus 50.225 into 10 to the power of minus 6. Then 33.4833 into 10 to the power of minus 6, 0, 0. We found all the displacement and rotations in a beam element at each node. After that, he has asked to find out the internal forces on a beam element. The internal forces on a beam element is in a shear force and bending moment. The shear force and bending moment at each element we need to find out. Shear force in a element number 1 and bending moment in a element number 1. Shear force in a element number 1 and bending moment in a element number 1 we need to find out. As we have the idea, internal forces on element number 1, SF1 BM1, SF2 BM2. This is the internal forces which is induced in element number 1. At node number 1 we have SF1, and moment we have BM1. At node number 2 SF2 BM2. At node number 3 SF3 BM3. SF means shear force, BM means bending moment. So these are the things which we need to find out. First I will consider element number 1. The internal forces is equals to K into Q. Stiffness matrix into displacement. We have this stiffness matrix into displacement. When we will multiply, we know the equilibrium equation, K into Q is equals to F. Separately we will take this is a K1, Q1, F1. If we will take for element number 1 stiffness matrix, displacement vector, and this is called as the internal forces. We have that idea. Then this internal forces F is equals to K into Q. 8.296 into 10 to the power of 6. This stiffness matrix we have copied. We have found this is a V1 theta 1, V2 theta 2. The V3 theta 3 comes in a element number 2. But element number 1 will get start from node number 1 and ends at node number 2. We have here V1 theta 1. We have here V2 theta 2. So only these values we need to take. Rest of the values will come for element number 2. We are concentrating to find out the internal forces in a element number 1, right? So after getting that idea, now you can easily get here internal forces. Multiply this row with respect to column. We are multiplying when we will multiply 4 cross 4 matrix into 4 cross 1, we will get a 4 cross 1 matrix. See here, with respect to this row, 12 into 0 plus 18 into 0 plus 12 into this value plus 18 into this value. When we'll take here, these first two values will go 0. Due to these two values is 0. Minus 12 into minus 50.22 into 10 to the power of minus 6 into this value plus of 18 into 33.48 into 10 to the power of minus 6 into this value. The total value of this is equals to 10 kilonewton. The shear force is induced at node number 1 due to the application of a force at midpoint in a beam element. We have F1 is equals to 10 kilonewton. Similarly, then next this value, second row, this column value, first these two values will go 0, and then minus 18 plus 18 is multiplied with this and add both the values based on the matrix rules and positions. We'll have a 12.5 kilonewton meters. Kilonewton per meters means it is a bending moment. We have this bending moment number 1 at node number 1. Similarly, this row is depends upon the bending moment. This row is depends upon the shear force. Why? This is a V1 and this one is theta 1. Similarly, this third row is depends upon a V2. We'll get a shear force at node number 2. This row number 4 is depends upon a theta 2. We'll get a bending moment at node number 2 with respect to row number 4. As usually, you have this idea to resolve this matrix. Resolve this matrix. After resolving that matrix, you will get a minus 10 kilonewton with respect to a V2, and with respect to a theta 2 moment we have. When you will resolve fourth row with this column, multiply it 18 into 0 plus 0 into 18 plus of minus 18 into minus 50.225 into 10 to the power of minus 6 plus of 36 into 33.48 into 10 to the power of minus 6 whole multiplied by 8.296 into 10 to the power of 6 is equals to 17.5 kilonewton meter. We have this shear force and bending moment at the element number 1. For element number 1, shear force and bending moment values we got, and similarly we need to find out shear force and bending moment for element number 2. We need to take this value, same stiffness matrix. We have the stiffness matrix, copy it, and then displacement vector element will get start from node number 2 and ends at node number 3. That means the transverse displacement which is start V2 and moment theta 2 at node number 3 V3 theta 3. So then V2 theta 2 V3 theta 3. V3 and theta 3 are 0. V2 and theta 2 we have find out. That value you substitute here and then resolve this matrix. You will get a shear force at node number 2, that is 2 2, and then this is 3 and 3. At node number 2 shear force which is equals to 0. Bending moment at node number 2 we have again 25 kilonewton meter. Shear force is 0 at node number 2, and bending moment which is equals to minus 2.5 kilonewton meter. When you will resolve these values, you will get this answer. This completes the part A of module number 3. All the topics I have covered. In next video, I'll take part B, torsion of shafts. Thank you for listening my lecture.